In this video lecture, we're going to see the Carathéodory extension theorem from which we can get existence of measures. We'll start with some motivation, in particular the Lebesgue measure. We have stated its existence and uniqueness and discussed its uniqueness already, but not yet the existence. Then we go and discuss finitely additive measures as more some type of object that we do not want to study here because they don't have the nice properties that we're interested in. From there, define what are premeasures. Premeasures are in opposition with finitely additive measures, and use premeasures to state the Carathéodory extension theorem. And we'll not prove Carathéodory extension theorem in full details, but we'll discuss the main elements and ideas involved in the proof, which is through outer measures. So as our motivation, let us recall we have stated this theorem about Lebesgue measure. It says there's a unique measure on the real line with the Borel sets that assigns to intervals their lengths. Knowing that a measure is expected to assign to each interval, let me draw them like this, to each interval their length, we already know if it is a measure, what is the measure that it will assign to a set that consists of the union of two intervals. It will have to be the sum of these two, because measures are additive. And likewise, if there are three disjoint intervals here, then again the measure of the set consisting of the union of these three intervals will again be the sum of these intervals. Then we can consider a measure on the whole algebra of given by unions of intervals of this form, and hope that by specifying what the measure has to be on that algebra, that this would define uniquely a measure on the real line. Unfortunately, this is not always the case, and this is the topic of this brief section, is to describe measures for which this fails and which cannot be extended to proper measures. So a finitely additive measure is the following. If we have a sample space and an algebra of subsets of that space, so an algebra is a collection of sets that is closed under complement, union, and intersection, but not necessarily infinite unions and infinite intersections like sigma algebras. And if we have a function, mu, that assigns to each element in the algebra, which are subsets of the sample space, if it assigns a non-negative number, including possibly infinity, we say that this function is a finitely additive measure if it satisfies assign value 0 to the empty set and be additive for disjoint unions, but only finite disjoint unions. We don't require countable disjoint unions as for measures. The first thing to note is that finitely additive measures, that's not a very good name because they are not really measures. And the theory of finitely additive measures, as we have discussed in the first part of this module, it is rather limited. Why? Because we cannot take limits there. We have seen that a measure which has nice properties in the sense that you can use it in combination with limits, it needs to be countably additive, not just finitely additive. And here's an example of a uniform measure on the set of natural numbers. If this is the set of natural numbers, then the chances that by picking a number at random from this set we get an odd number is equal to a half. And we can think about this chance of a number being an odd number as being equal to a half in the following way. We take a very long interval, we pick a number uniformly at random from that interval, we compute the probability that the number will be odd, and if we make this interval larger and larger and this probability converges to something, we call that the probability that a natural number chosen at random satisfies a certain condition. So it is in this sense that we say that a large number that would pick at random has chances 1/2 of being odd. And likewise, if we pick a year at random, the probability that this year is a leap year, it should be 97 out of 400, and that's because, well, every 400 years we have a cycle, and 97 out of those 400 years will be leap years. So as I said in the beginning, this would be in some sense a frequentist notion of chance. So the chance that we observe a certain event, the chance that a natural number belongs to a certain set, will be the number of points of the overlap of that set and the beginning of the real line, or the first n natural numbers that we can place here on the real line. We divide that by n, take a limit, and if that limit exists, we'll call it the chance of a number belonging to the set A. And surprisingly, it turns out that this notion is finitely additive. For instance, if leap years are always even, so they're not odd. Okay, so the chances that a year is odd or a leap year, it should add, because since these two events, they are mutually exclusive, they are disjoint, so we can add the probability of being odd and the probability of being a leap year, and this is the chance that if we pick a year at random, this year will be either odd or a leap year. And likewise, the chance that a year is not a leap year will be 1 minus the chance that it is a leap year. So it will be 400 minus 97 divided by 400. This is the chance that a year is not a leap year. And this is a very bad measure in the following sense. It is discontinuous. And here is a simple example to show that it is discontinuous. We take the set A, An, to be the set where we eliminate the first n minus 1 numbers from the natural numbers, and we include the next ones. And if we want to compute what is the probability that a number chosen at random is in An, according to the previous definition, it will be 1. Because as we make this interval larger and larger, the probability that the point we pick will be on this part, this is getting close to 1. So mu of An, for this An given by this, is 1 for every n. However, as we make n tend to infinity, we see that every point is eventually going to disappear, and the sequence of events An, it is decreasing, and its intersection is the empty set, and the measure of the empty set is 0. So we see that this property of continuity from above does not hold for finitely additive measures. So in this module, we'll work only with sigma additive measures and call them simply measures.